Hello everyone, welcome back to the channel. Today we're covering the first law of thermodynamics, and this is genuinely one of the most important results in all of physics because it's really just a statement of energy conservation, and you can apply it to systems that exchange heat and work in their surroundings. And what the first law says is that the change in a system's internal energy, which is denoted by U, equals the heat added to it, Q, plus the work done on it, W. And what makes this useful again is that internal energy is a state variable, so it only depends on where the system starts and where it ends up. But heat and work individually depend on the exact path taken to get there, so it simplifies calculations. And today we're going to work through 3 examples, starting with a basic application of the law, an isobaric expansion using the work integral, and then a full cycle on a PV, a pressure volume diagram, which ties everything together. So let's get into it. So let's start with question 1. And I'm just going to quickly write out what the actual first law of thermodynamics is. So U is equal to Q plus W. And that's literally it. And if we want it as an infinitesimal form so that we can do integrals on it, we can say a change in U, a very small change in U, is equal to a small change in Q plus a small change in W. And this actually stems from simple energy conservation. So in a closed system, what is the internal energy of, let's say, a gas? And if we're not doing anything to this system, it is literally just the heat. So when work is 0, the internal energy is simply, the heat energy of the system. That's it. And if we start doing work on it, like, compressing it, that turns to a work done being added to the system and more energy being added or taken away depending on what you're doing. So you just simply add a work done. And to a closed system, that is all the energy in it. So let's start with the first question, applying the first law. A gas in a closed system absorbs 500 joules of heat, while 200 joules of work done is done on the gas. Calculate the change in internal energy of the system. So this is pretty simple. If we just define what the values are that they give us in the question, we see that Q is equal to 500 joules. 200 joules of work is done on the gas, so that means the work done on the gas is a positive 200 joules. And using the simple first law, energy conservation, we get that U is 500 plus 200, and U is simply equal to 700 joules. So if we now look at question 2, we see that it involves an isobaric process. And an isobaric process simply means that there is no change in pressure on the system. And actually there are other terms relating to volume and temperature. So a constant volume is known as an isochoric process. Constant temperature is known as an isothermal process. And that will change exactly what you're doing, but the concept of solving these problems is the same. So let's read through it. An ideal gas expands at constant temperature P, which is 2 times 10 to the 5 pascals, with its volume increasing from V1 to V2, which are 0.01 meters cubed to 0.015 meters cubed respectively. Calculate the work done on the gas during this expansion. So we want to solve for work done. And actually here we can see that we don't get given U or Q, so we can't use the standard form of the first law. But how can we write work done in terms of P and V? Well, we know that work done is force times distance. That I hope everyone knows. And what is force? Force is equal to pressure times area. So if we rewrite this, work done is pressure times area times distance. Cool. Now we can just use a tiny bit of dimensional analysis, which I've actually made a video on if you want to check that out. But area is meters cubed. Those are the units for area. And distance is meters. Those are the units for distance. What is meters squared times meters? Well, that equals meters cubed, which is a volume. So, work done is pressure times volume. But now we want to change in work done. And we know that pressure stays the same since it's an isobaric process, but the volume varies. So we can write this in terms of P dV, and we have two different volume values, which it changes continuously by. So we can simply write this as an integral from V1 to V2. And finally, since the gas is expanding, it's doing work on the environment's not doing work on the gas, therefore we can add a negative sign. So this is pretty simple calculus. Changing W is minus. I'm just going to write it in terms of the values it gives us. 0.15, 2 times 10 to the 5 dV, which again is equal to 2 times 10 to the 5. I'm just going to write it to make sure I don't mess it up. Cool, so that is minus 2 times 10 to the 5, 0.015 minus 0.01, and that gives us minus 1000 joules. Moving on to the final question, we're going to be looking at solving a full cycle on a pressure volume diagram. So let me explain what that is. On the y-axis, we write pressure. On the x-axis, we write volume, and we see how they relate to each other at different points in a cycle. So in this case, a gas undergoes a cyclic process consisting of 3 steps. Step 1, isobaric expansion from state A to state B. So isobaric means pressure is constant. So we say this is A, and we're going to state B. Since the volume is expanding, we can draw a line connecting those two. Now step 2 involves an isochoric pressure drop from state B to state C. So that's a constant volume with decreasing pressure. So this would be state C. And step 3 involves an isothermal compression from state C back to state A. And you might be wondering, well, how the hell am I going to draw this isothermal thing? I don't even know what that is. But look at a fundamental equation that relates all the terms we are trying to kind of solve for. And I'm hoping everyone knows this ideal gas equation. Pressure times volume is proportional to temperature, considering these two stay constant, which they do in this scenario. We can assume that they do. And that means that pressure with a constant temperature, since it's isothermal, is proportional to 1 over V. And so therefore that graph looks like kind of hyperbolic curve up. That is a rubbish curve, but that's what it looks like. And that connects C to A. So what does part A want us to do? Let me just cut this off. Okay. Part A wants us to verify that step 3 is a genuine isotherm by checking that PV is equal at states A and C. Now, why does that tell us that it's a genuine isotherm? Well, since we have discovered that this is a constant, PV at state A should equal PV at state C if it's an isotherm. So let's solve that. PV state A is equal to 2 times 10 to the 5 times 0.01, which is 2 times 10 to the 3 Pascal meters cubed, and PV 1 times 10 to the 5 pascals times 0.02, which again gives 2 times 10 to the 3 Pascal meters cubed. Therefore, it is isothermal compression. Okay, part B. Calculate the work done on the gas during each of the 3 steps. Sure. So the first one is isobaric expansion, and we've already done this actually in the previous question, but I'm going to rewrite it again. So work is minus P dV, and if we want to integrate, we can do dV is equal to minus the integral of P dV, with P being a constant and volume changing. And so what is this integral at state A to state B? That is 0.01 to 0.02 times the pressure, which stays the same at 2 times 10 to the 5 dV, and that again is, just going to write this all out, and if we type this into a calculator, we get minus 2000 joules. So for A, W equals minus 2000 joules. For B, an isochoric pressure drop. Now, what's interesting about this is, since the change in the work done is equal to minus the integral P dV, and dV equals 0 for an isochoric process, the work done is simply 0, so it doesn't contribute. And now for C, work done for isothermal compression. So again, we rewrite this. But here we can see there is no T dependence whatsoever. And that's kind of an issue if we're working with temperature. So how can we rewrite this? Well, again, PV equals nRT. And this is a constant. P is equal to nRT over V. And we can substitute that into the work done. So dW is equal to minus nRT. Since this is a constant, it doesn't have to go into the integral. Integral V1, V2, 1 over V dV. So let's write this out. dW is minus, and we know that actually nRT is equal to 2000. And this is because nRT is a constant in this case. And we solved at state A that PV is equal to 2000, since we can see that 2 times 10 to the 5 times 0.01 is 2000, and that's equal to nRT, and that nRT is a constant. So we can say that nRT here is again 2000, and in this case we're going from C to A, 0.02, 0.01, 1 over V dV, giving us W is equal to minus 2000 ln 0.01 over 0.02. And if we calculate this, we get 1386 joules. Perfect. So now the final part, part C. We need to find the net work done on the gas over the full cycle and state whether this is consistent with a clockwise or anti-clockwise cycle on a PV diagram. So finding the work done is pretty simple. We do total work is work at A plus work at B plus work at state C minus 2000 plus 0 plus 1386, giving us minus 614 joules. Now, how do we interpret this? Well, the net work done on the gas is negative, meaning the gas does about 614 joules of net work on its surroundings over a full cycle. And plotting this on a PV diagram traces out a clockwise loop. since it goes, from A to B is right, then B to C is down, and then C to A is kind of up and left, back to the start. And this means that clockwise cycles means that the system does net positive work outwards, which is the behavior of a heat engine. If it was anti-clockwise, it would do net positive inwards, which would be a heat sink. So thank you for watching, and go practice yourself.